Hello. All right. So today we're going to talk about how to verify distributed systems. We all want to build really cool things, but at the end of the day, if our customers are unhappy because we're having an outage, we're all going to have a bad time, and we're probably not going to have a job for much longer. So let's get started. So I'm Caitie McCaffrey. I'm a distributed systems engineer. I work at Twitter. This is where you can find me on the internet. My DMs are open on Twitter, so if you have a question that you don't want to ask publicly on the internet, feel free to shoot me a DM. I totally like to talk to people on the internet. I think it's fun. So yeah, let's get started. So I wrote this article that was published in ACMQ at the end of last year and was also published in the Communications of the ACM in February of this year, and it's called The Verification of a Distributed System. And so this is like the talk format of this article with a lot more fun stories and maybe a little more ranting because you have to keep your shit together when you write for the ACM. So if you would like to read this, it's online or after the fact. But yeah, let's get started. So the motivation of this is, this is a distributed systems talk. So let's start with a quote from Leslie Lamport, because what talk about distributed systems is complete without one? A distributed system is one in which the failure of a computer you didn't know existed can render your own computer unusable. So this is how Leslie defined distributed systems back in the day. But this is obviously not acceptable anymore, right? You can't just be like, oh, this computer on the internet went down and sorry, we're having a major outage. You can't tweet or play Halo or watch Westworld. That's not cool. So we have to do better these days. And so this talk is hopefully going to help increase your repertoire of different tactics that we can use and maybe give you some more, change your perspective on different things of testing that I used to think were not that valuable. I just want to also briefly pause to say, today we are all building distributed systems, so even if you're not working on a distributed database or writing an implementation of Raft, we all are. It could be something simple where you have clients and a horizontally stateful service or stateless service and then a database that you're talking to. Or it could be super complicated all the microservices that we have at Twitter, and this is one of our call graphs from Zipkin. Or it could be something that you happen to inherit that's a bunch of things duct taped together. This is from Coda Hale. I stole this from him, or borrowed it, I should say. But these things have to work, right? They have to work because presumably you have customers or you are building this for a business of some sort, and we want to make our users happy. Okay, so how do we do this? In this talk, we're going to start with a really quick overview of formal verification. I think it's interesting. This is the academic term. Inez mentioned it in her talk as well, just in case you haven't seen it or you want to go down that rabbit hole. Then we're going to talk about things that I think are a little more practical that you might actually use. I call this testing in the wild. This is things that will give us the confidence that our system is correct, but it's not mathematically provably correct. And then I'm going to talk about some research that I think is super cool that's happening because I really like partnerships with academia and industry. I do a lot of tech transfer stuff. And this is sort of where I see hopefully research can help us and make our jobs as practitioners easier by providing better tools so that we can verify our systems more easily. I'm going to go really quickly through a bunch of stuff. I have a repo on GitHub which has all of the references for this. Don't worry about trying to get the URL. I'll tweet it out after and it'll be on a slide bigger at the end. But don't worry about trying to take notes. And yeah, let's get started. So formal verification. So this is the idea that our systems are provably correct. And what it's doing here is it's using typically propositional logic, some form of that propositional logic, and mathematics to prove that the system is correct. We'll go through a model checker or through a theorem prover, and then at the end of the day, what comes out is it works because math, right? So that's cool. This is the holy grail. So what you typically will hear are formal specification languages, and two of the more popular ones that you might have heard of are TLA+, which Leslie Lamport invented, and COC. And so the idea here is that you write your specification in some form of propositional logic. These are all sort of domain-specific languages. And then, or they have their own language, and you write it. And then you either use a proof assistant to prove that it is correct, or you run a model checker, which will exhaustively check the entire state space of inputs into the system and then prove that it is correct. These model checkers take a long time to run, so they're not ideal. But it's not actually that terrible. You hear a lot of horrible things about formal specifications. This is an example of TLA+. This is an hour clock specification. It's actually from this PDF book that Leslie Lamport wrote that's online for free called Specifying Systems. And what he did is in propositional logic, he defined an hour clock. So this is just the idea of if you have a clock that just tells you what hour it is, and it only goes from 1 to 12 and then like back again, because it's not a 24-hour clock. So what he says is we have this variable hour, right? And it extends natural numbers. So that's, you know, all positive numbers. And then in addition, we go and we define hours. We break hours down to be only the numbers 1 through 12 in the natural number set. So we've already limited our space there. And then we basically define how hour can change. So the hour can change if it's 12, it should go back to 1. Otherwise, it should be, you know, the next hour prime should be hour plus 1. And then you go through and you add this time information, and this basically proves that if you like that an hour clock written to the specification is correct and will only display the number 1 through 12, and then roll back again. So that's cool. It looks kind of like code. It's not that scary. Why I actually mention it in this talk is because Amazon in 2014 released a paper discussing how they use TLA Plus to verify 10 plus core pieces of their infrastructure, including S3. So this is really cool, I think, because Amazon actually took the time and they went and had a bunch of engineers learn formal specification in TLA+. Like, this is a doable thing. You don't have to be an academic to do this. And then they went and they wrote the specifications for 10 core pieces of infrastructure. And they say that this was a huge success for them because in their planning meetings and when they did a retro of like this whole investment of time, and they said basically they found 2 really serious bugs, which sounds like nothing, except for the fact they think they would have never found them otherwise. So this is reducing the unknown space if you went to Inez's talk before, because they wouldn't have found this. This would have been a catastrophic incident that they would have only discovered after the fact. The other big thing that this gave them is it increased their confidence to make really aggressive optimizations in their system. And so they were more confident in making these really aggressive optimizations to reduce cost or performance, and they still knew their system was correct because they had this proof, this logical proof that told them it was correct. So Leslie Lamport also says in specifying systems when talking about TLA+, just like it's a good idea to design your system before you build it, like we write a design doc, or if you're a test-driven developer, you like TDD, you might do that, and that's like sort of your design for how the system should work. Whatever thinking about your project up front you do, specifying using TLA+ is another one. It will help clarify your understanding of the system and therefore expose bugs to you because you're being forced to think about this in a very rigorous manner, right? And so what they actually found in the Amazon paper is that they discovered a lot of these bugs by just writing the specifications. They didn't even put it through a model checker or through the proof assistant because their engineers just had to think about it so rigorously that they then realized, hey, there's a hole here that we missed, and here's an edge case we missed. And they were able to correct the bugs that way. So that's pretty cool. The biggest complaint about formal methods tends to be that you are writing a proof in something that is not code that you can execute. And so that's problematic, right? Because you spend all this time, you write this whole proof, you're like, it's perfect, and then you're like, someone has to go implement it. And obviously, we aren't perfect at implementing things, right? Like, that's where bugs come from in the first place. And then your test case, or your code that you now write, like, could have a bug in it, or maybe the runtime doesn't have the same assumption baked into it that you wrote in your specification, and so, like, there's this impedance mismatch of, I spent all this time doing this thing, but I still have to write code which could have a bug in it because I'm not perfect at translating. But what is interesting is that if you use Coq, which is a different language, it actually can generate, you can actually extract code in OCaml, because it runs a subset of OCaml. So it's not a Turing-complete language, so you can't do everything, but you can do a lot of things. And so at POPL, which is a conference, a programming languages conference, this year there were 2 papers that were published that actually went and implemented something in Coq and then extracted the code and they ran it. So I think this is super cool because basically we've now gotten to this, or we're starting to make progress in the space of, I write a specification, I know it's actually absolutely correct, and then I push a button and all the code is generated and then I just deploy it and it runs. That's pretty cool. So what they did, just to give you a quick example, one of the papers was they went and wrote the Raft consensus protocol. You may be familiar with Raft. Raft is a consensus protocol. It's like Paxos or Zab, but it's a more understandable one. And there was actually never a rigorous proof done of it because like it just, the guy didn't have time, he like graduated. So, so what some grad students at UW did, I believe, University of Washington, yeah, is they went and they wrote the proof in Coq, and then they actually generated the code and they ran it as a consensus algorithm, and it worked, which is cool. I mean, and so this isn't talking about performance, and we're not going into that, but just the fact that we are getting good enough that we can have take more of a semantic interpretation, which is this formal specification, and generate code is really cool to me and really exciting. And then there was another one where they also went and they wrote a database, a key value store in Coq. They generated the OCaml, they deployed it, they ran it, and I think they ran some benchmark against it. It was pretty slow, but like this is actually an exciting world because you can then start thinking about, well, this is another area of research where compilers can go and optimize this. So I think that gives me a ton of hope for the future, but like, what are we doing now? Because we're like in this world where I don't have that, and like I have to hit my deadline and ship some code and like do things that make people happy. So how do we, get from formal verification to like seems pretty legit, like ship it, right? Okay, so I'm gonna go through a bunch of stuff that I use in my day-to-day and that I hope either you are already using or, and then we'll go through like into the more like artisanal stuff, I guess. It's actually not that hard at the end that you can implement into your day-to-day life or hopefully take back to your teams and implement and increase the confidence of the systems you're making. So unit tests, I think everyone is familiar with unit tests. I'm just going to briefly define them as like, this is a thing that can be ran as part of your continuous integration. It doesn't require an environment. It just needs like CPU and a computer to run on. This is super useful for verifying basic functionality and error cases. This is something you're basically taught as a software developer, like write unit test cases. So fine. Do that, but the reason I bring it up in this talk is because there was this great paper in 2014 that came out, and this was another great partnership of academia being interested in what is happening in industry today. So these researchers went and they analyzed 5 open source systems, Cassandra, HBase, HDFS, MapReduce, and Redis. So these are all open source. They went and looked at the code and looked at the error logs, or sorry, the bugs that were filed for all of these code bases, and they randomly sampled 198 bugs. And then they went through and they sort of like tried to reproduce all of them or figure out what the fix was. And then they wanted to come up with some conclusions, because the goal of this paper was to understand like where can we dedicate research effort into helping practitioners do a better job of making reliable systems. They also picked a very heavy sample of catastrophic failure, and catastrophic failure means data loss, huge outage, et cetera, so like real bad times. Okay, so one of the things that they found, one of the core things that was super surprising to me when I read this is 77% of the production failures could be reproduced by a unit test alone. So while that sounds a little snarky, it does lead to that we could do a better job of unit testing, but what it does give me too is some of this is like you can't be totally clairvoyant, right? Every unit test possible, right? Like we're not gonna do that, that takes way too much time. Now we're going into the model checking realm. What it does mean, though, is that when you do have a major outage, I think it's worth spending time thinking about what unit tests could we add to our CI or to our test passes to verify that this never happens again. It's actually not the worst to reproduce. You can't actually prevent this from happening by just adding a unit test case. This is the more actionable thing, I think, where they found 35% of the catastrophic failures were caused by what I like to call developer laziness. Its error handling code is simply empty or only contains a log statement. Error handlers abort the cluster on an overly general exception. So this one's kind of harder to catch, but it's basically just they're like, catch any exception and just like throw and like everything barfs. And then there's also the error handler, which is contain comments like fix me or to do. I mean, I worked in a code base once that had like this really great comment that I found like straight out of school that was like, hey Joe, please fix, okay, thanks, bye. And I was like, cool. So that's really problematic, right? That like this is stuff that's actually pretty low hanging fruit that we could go and fix on our own. I also thought what was interesting is they found other things that were basically like most of the bugs, 58% of the catastrophic failures, so more than half, were actually caused by improper testing of error handling code that could catch this. So for me, what I've done with my teams now is we actually use code coverage. I was always sort of like on the fence. I'm like, like whatever, it's like a thing, like no one cares. But what code coverage does tell you is if there are big gaps, and especially if you can have it run as part of like your code review process, if you check that at least the new code introduced actually tests all the error handling, you're going to have a better idea that like your developers have rigorously thought through like, hey, what could go wrong?
because it's actually really not that hard to write the golden path scenario. We're all really good at that at this point. When it gets to distributed systems, though, when like stuff hits the fan, right, like is when the error case happens. And that's the part that's actually harder to think through and generally takes more time. And so it should have a test case to go along with it. Okay. I'm going to pause really quick and have a bit of a rant-a-festo. Types are not testing. Yeah. So I actually really like typed languages. I actually don't really like dynamically typed programming languages. I program in like everything though. Like I've shipped code in 10 plus languages, so like whatever. So I just want to put my bias out there. I really liked typed programming languages personally. But they are not testing because types can only basically verify at compile time the expressiveness of your type system. And we don't have any type system out there today that can capture the semantics of what you meant. So this is a really dumb example in Scala where I made a function called add, and instead it actually multiplies. So this seems super stupid, but there's like all these things where like the type system is like, it's cool, but like a test case would catch this, right? Another fun fact that's like maybe more real world is I was doing a code review with a younger developer. And he was super into type systems, and he really liked type theory, and he was like, yeah, like, you don't have to you don't have to write test cases, you don't have to like do all this like boring stuff. And then he like submitted this code review, and he's like, I don't need tests, the type system prevents me from needing a test here. And I was like, okay. And so I'm like doing the code review, and I actually found an infinite recursion bug by just doing code review. And so I like, responded back, and I'm like, hey, I think you don't have a base case. I don't think it stops recursing if like it just retries forever, and that's bad because your stack will blow up on the JVM and then like sad times. And so I just added this comment pointing it out, and I was like, hey, could you please at least like add a test case that the code stops recursing. We don't blow up the stack. And he was like, oh yeah. And so I like hope at least that made an impression on him that like, right, like type systems are not the end all be all. They are not expressive enough yet for us to not have to write test cases still. Also, TCP doesn't give a shit about your type system. So, and this comes back to, distributed systems where it's like, right, we can maybe like build something that compiles and runs on one machine and is like correct. Maybe we'll get there soon. But like going over the wire, like all bets are off because you have asynchronous networks, you have partial failure. And so when we come to distributed systems, we are not in a world where we can just write a bunch of Scala or Haskell or like whatever type system or type programming language you really love and not write any test cases. So this sort of brings me to my next topic, integration tests. So this is basically, you have a bunch of nodes, you might have some tiny environment, whether that's a bunch of Docker containers running on your local machine or an actual deployed environment in the cloud, and they talk to each other. So this is super important because integration tests are really testing the boundaries and like these assumptions you've made, generally between other teams. And so one of my favorite integration test stories that we caught when I was working on Halo 4 is I was running the statistics service, and we actually did a rewrite of everything. And because of reasons that I'm not going to get into. But what we did is like I was launching the new service in our developer environment, and all the game clients started hitting it. And I noticed this thing. I'm like, the game's sending us the stats at the end of the game of like, how many headshots and did you win and all the wonderful things you did if you're really good at Halo. And it would upload them 3 times, like they kept failing. And I'm like, this is super weird because it's totally returning a 200 and saying it did it. And so the network developer and I argued for like 3 days, I think, over this about whose fault it was, like whether it was my fault or whether it was his fault. And then finally at the end, I had this like, just because I had like gone through spelunking in the old code base, I found this thing where in the payload, the old code base actually used to put the word done in all caps exclamation point in the payload response. And so I put that in, and then they only sent it once miraculously. And I was like, oh. That's cool. So the spec on the old game was actually like, they didn't have it. I mean, this is like an old Xbox game. They didn't actually have like proper HTTP. This has nothing to do with the old game being bad. It was just the spec that I was building for was different than the spec the game code was operating on. So we actually did fix it, and it looked at the HTTP 200 and the new code. But this is like how you test those boundaries and expose all these assumptions that we make. Okay, the other thing that I think, going back to the simple testing can prevent most critical failures paper that they discovered, is 3 nodes or less could reproduce 90% of the failures that they saw. So this is super huge. Like this totally blew my mind because I was sort of always under the impression that you needed a production scale system to reproduce these catastrophic failures. And it's not true. You actually don't. This is like the level of like, I can run this on my laptop, right? I can run 3 nodes on my laptop and test them and inject failures, and which we'll get to, and then prove that this system is still reliable. So we can do a better job at a lower cost.
And we don't have to build out these huge staging environments. We can literally run really small scale ones. Okay, so that's sort of the basics. What I want to get into now is this other form of testing which I really enjoy. It's called property-based testing. It's actually inspired by model checkers in formal verifications. So the idea behind a model checker is you have a state space of all the inputs, and it's huge, and you run all of them. And property-based testing takes that idea, except for it just sort of randomly generates the input and into the properties that you define. And so you can like limit it to run like 100 test cases or 1,000. And so then it's not like going to sit there and run for days. It'll just run for a couple seconds. So this is really cool because it's actually very accessible now. Like this is one of the things that I started doing with my current team. And it actually helped us find a bunch of bugs, partly because it forces you to more rigorously think through your test cases. But basically the way this started was with quick check. And quick check was invented by John Hughes. And so basically what you do is you define this specification instead of a test case, and I'll show you an example. It's really not scary. And then you have a tool that generates all this input. And then if it finds a failing case, it'll report it to the user. And what quick check does, and Scholar Check, and most of these have, is something that will then like reduce the state space. Like if it took 1,000 inputs for it to find the error, it'll actually shrink it to the smallest number so that you don't have like cognitive overload trying to debug step through like 1,000 different inputs. Quick check has been actually super popular in industry. REAC, which is a distributed NoSQL database, used it to model their eventual consistent data store, and they found a bunch of bugs. There's a bunch of really cool talks that I link in my references section. In 2015, John Hughes published a paper about how he used quick check to find bugs in Volvo cars. So this is something when we start talking about like real objects that are operating in the physical world that like have an impact on people's like mortality, maybe we need to be more rigorous with our testing. And then he also in February 2016 published a paper where he used it. He works in conjunction with these things. It's not like he just goes around and breaks stuff and then like laughs at people. He ran it in Dropbox against Dropbox and found a couple really critical bugs. So this is really cool. So yeah, you can do it. There's one, Scholar Check is great for the JVM, and then there's like all of these like implementations for like pick your favorite language. I'm using it in Go right now, so that's cool. Anyway, this is a Scholar Check example just to give you an idea of what it looks like. So the first one is basically saying that all of the integers are between 0 and 100. This one's super stupid, I think, but it just shows you the outline. You just say, for all of the integers that I've input into this thing, make sure that they're between 0 and 100 and like return false if it's not. So that's trivially going to pass. What I think is more interesting is the second one, where it says reverse a linked list, or reverse a list, right? And the reverse of the list should equal the list. And so this is cool because like for things where you're doing reverses or translations and serialization and deserialization, you can like generate all these like really complex objects, throw it through the serializer, deserializer, like Scholar Check or whatever will do it for you. And then you can find if you have any weird edge cases, like, oh, I didn't know there was going to be like a nil there. For instance, I am using this with thrift. So we use thrift at Twitter to communicate as our binary format, and so we serialize it into an application object, and then we like to serialize it back out. But I'm using, because we're writing some Go, which I'm less familiar with the Go thrift implementation because I haven't been using it as much, I like wasn't sure what it set some of the defaults to, and so I just wrote a property-based test and then like ran it, and I was like, oh, like that's a nil pointer, cool, like fixed, and then like we kept going. But it was super easy and super fast, and this is literally like the same amount of effort as running a test case, except for you get to explore a much larger state space. So this is one of the ones that I would highly recommend using if you are not already. Okay, so this one is fault injection testing is, I think, super critical for distributed systems because what we're doing is like the idea of resilient systems and having something that can stay up and survive a failure is that it survives one machine or more being down. And so if we don't explicitly test that, there's no reason we should have any confidence that it'll operate correctly in failure modes, right? Like if you don't force the system to fail, like why do you think it's going to work at 3 a.m. when the data center goes down? If you've never tested that. This is the stuff that's really, really hard to get right. So fault injection testing, I think, is really interesting because there are once again a wide range of a wide spectrum of like investment in terms of like time and money that you can spend into using fault injection testing, and the results are generally like really positive, even with the lowest level. You find a lot of bugs. So
Netflix has a simian army. I think people are pretty, used to this, but this is a kind of fault injection testing. So Chaos Monkey killed an instance that injected a fault by taking down a node. They also have Latency Monkey, which introduces artificial latency into the system. So that's injecting a fault by like delaying a message or dropping a packet. And then Chaos Gorilla took down an entire availability zone. So that's how they're testing that their systems stay up. Another one that I think is super fun is Jepsen. So Kyle Kingsbury runs Jepsen tests, and what he does is Jepsen is a tool that injects faults into a network partitions, and he tends to test a lot of databases, right? So he's tested Mongo, he's tested Kafka, he's tested Cassandra and VoltDB, and you can now pay Kyle to test your databases if you want to do that, or your systems. This is all also open source. You could go use it if you wanted to as well, and he has documentation. But basically, Kyle started this as a side project because he really liked distributed systems and was like, hey, there's like all this great stuff that's open source out there. But he was like, I don't really see a lot of proof that these databases are like upholding the claims that they guarantee, because like, where are the test suites? Like, who proved this? Like, where's the verification? And there wasn't any. So he sort of started with this nice, like, here's the world we live in, and we thought it was all fine, but it really looks like this. And so like he has found a lot of really catastrophic bugs in a lot of really big databases and open source projects. And the good news is that Kyle basically goes and tests these and then files very detailed bug reports, and usually these things get fixed. So like I think he found a bunch in Mongo and then like filed all the bug reports. A lot of them got fixed. He retested it. He found a couple more, but like they're making progress in the right direction. So the purpose of all of this is not to like shame people for getting anything wrong, because what we're doing is fundamentally very, very hard. It is to help us learn and get better and grow and evolve how we build systems and build better systems in the future. So I really like this project. The blog posts are also really interesting and a great education. If you want, go to the early ones. They have like really funny pop culture references. They're a little more buttoned up now that he gets paid to do this. So anyway, but yeah, so these are great. I just want to pause really quickly and say, doing all of these things, unit tests, integration tests, fault injection tests, and none of these ensure that your system is correct, right? We aren't the gold standard of formal specifications, but it does greatly increase our confidence. So you may do all of these things and be like, it's perfect, it passed a Jepsen test, like it must not have any bugs in it, and that's not true. That just means it didn't find any bugs, right? And so we have greater confidence that more of the state space has been explored, and so that we can, that we have a greater confidence that we like have shrank that like unknown amount of stuff that's going to happen to be very small. Okay, so another one that I think is super interesting is game days. And this not only tests your infrastructure and your systems, but also your process, which I think is really important, especially when it comes to operations. So game days were developed by Jesse Robbins at Amazon in the 2000s. He actually had this really cool title called the Master of Disaster. And so what he would do is he would tell engineers, in 3 to 4 months, there's going to be a major outage. And then he would take it out of a data center in like some weird way. Like one time he actually mimicked a fire in a data center to eliminate a significant amount of capacity. And so what the purpose of running a game day is it helps you uncover hidden dependencies. So they talk about one time they took out, a Sao Paulo data center and one in Mexico got affected. And that's super weird. Or they like took out a data center and it actually was the only data center that their paging ran out of, and so they got no pages. So that's really bad. But these are things that you're finding and you're doing in a controlled environment, so it's not as bad. And it's also like not at 3 in the morning. And it helps you test your process. So how do you run a game day, right? So first, it is crucial that you tell people you are doing this. Do not just be like, I'm going to run a game day, like pull the plug. Tell people, because the idea here is that just by communicating failure, by putting it at the forefront, right, it makes people think about it. And therefore, they're going to like harden their designs and really think about like, oh, if that data center goes down, like what might break? And so they can get prepared ahead of time. People also hate you less. You then induce the failure at some predetermined point of time. You monitor the systems under test, and monitoring is a critical component to this. And then typically the way they run this, if you're running it formally, is you have an observing only team. So they're not doing anything. They're not touching laptops. Well, they might be touching laptops, but they're not touching computers in the prod system. They're not mucking with any of that. All they're doing is they're sitting there in the war room or like on whatever chat channel you happen to use to deal with incidents, and they're watching what happens. And so like they're taking detailed notes because like even if something goes down in production and you know that this outage was like planned, your customers are still paying you, so you have to kind of get it back up, and that's scary. So what they want to do is have this team that's not worried about the outage, that's actually looking at the process and how everything's handled and taking notes, and then they're filing bugs about like what was actually broken. Like, hey, we like lost this link here. Hey, like these two teams don't even know who they are and they have a hard dependency on each other. Like maybe there should be something in the run book that says like, here's each other's email or something. And then for this to actually be appropriate, you have to prioritize bugs and get buy-in across teams to fix them. So, you know, like if you run it and then like do nothing, obviously it doesn't work. Another really great example of running a game day that was not super involved or complex was Stripe did this, and they ran one, I think this was in what, like 2014 or something, and they, 2014, and they ran, basically what they did is they ran a game day, they planned for this, they did the whole thing, they took a backup actually of their primary data center like right before they did it, so if anything went wrong they could, you know, recover, and so they ran kill 9 on the master node in their Redis cluster and it lost all its data. Because what actually happened is the node went down and then like it started to elect a leader, and then the master node came back up and it was like, hey, I'm still the leader and I'm still alive and I have no data, so like all of y'all should have no data, and then like the entire data set was gone. So that was cool, I guess. And then, so, but at least they figured it out that this was happening, right? Like, and so what actually was the root cause of this is that they, the Redis author had said that it used a configuration setting he wasn't expecting people to use. So this is, you know, if you go back to Inez's talk, like there's a lot about like reducing state space and tester configuration, because these are where all the weird bugs are, actually. It's not in the like, hey, the thing that everyone does 90% of the time, that stuff gets caught really fast. This is a really great tweet from Kelly Somers that I like, where she says basically like, even running a simple kill 9 test needs to happen more often in industry. Like we aren't doing this enough if this, you can find a catastrophic failure like this so easily. So this is something you can really, really easily do. And now I would like to take a break for another brief rantifesto about testing in production, because that was ran in production. And you know, so there are a lot of things where testing in production is super valuable, and Netflix runs testing in production, all of these things. There is also a lot of valuable information from fault injection that can be gained by testing in test environments. That could have actually been reproduced in a staging environment and never impacted users. And so it's always this risk versus reward trade-off that's happening here when you want to test in production, because at the end of the day, we are paid to make money and make our users happy for the services that we are providing. So if you want to test on your users and treat them like your guinea pigs, they might not be really happy. Right, like going back to that other paper that we said where you can reproduce most catastrophic failures on 3 nodes, I think this combined means we should do a little more staging before we just like kick things out into prod and then say like, hope for the best, right? Also, like monitoring is not testing. People say this to me, and I think it's because I work on Twitter's monitoring system, but I like don't know why. Like monitoring is super crucial for operating a distributed system, but it doesn't tell you anything about your system, like your system is verified before it goes into production. Monitoring is 100% testing on your users. It is totally reactionary. Like if you just like roll the whole cluster and then like the success rate drops to 0, like your users are still gonna hate you. So like don't do that. Like monitoring is not enough. It just tells you how to like correct the problem. It doesn't tell you that you don't have a problem before you ship. Okay. Canaries are super great. Canaries are also like, you may have heard green-blue testing. There's a bunch of different names for this, but the idea here is that we slowly roll out changes into production. And this is actually really, you know, I mean, it's like a verification in production because it's like already in production, so what are you doing besides testing on your users? But it is a way to actually greatly reduce the risk of deploying new code. So like continuous integration helps us like reduce risk by pushing smaller changes. Canaries help us reduce risk by pushing changes out more slowly. And so you can do this either manually or like build some automation around it. I do this with all of my teams when we ship code. We don't just like roll the whole cluster. We like, you know, slowly roll it and then monitor a couple canaries and then check out if it looks really bad or not. And then we'll roll back if it does. I want to caveat though, canaries only test that the new version is performing as well as the old version right now. right? Like if there is not a partition happening, it tells you nothing about how the new version performs under a partition. If there's not a leader election happening, it tells you nothing about how the leader election performs. If there is not massive traffic, it tells you nothing about how the new system compared to the old system performs at peak traffic loads. So this is a huge caveat. I think people in industry like have found canaries and they're like, it's a magic solution, you just deploy and then it'll like magically roll itself back. And I'm kind of like, yeah, except for when the problem doesn't, like these infrequent problems like leader election or major outages happen, it's because you didn't actually ever test that it did that. So like do that before you push it to prod, especially on these super dangerous distributed systems things. Okay, so we went through a variety of ways of how to test and verify systems in the wild. We have unit integration tests. This should be the base case. Like I'm really kind of tired of people saying like, oh, I don't write tests, it's boring, or like type systems or tests and blah, 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 blah. Like whatever, like it sucks, I get it. Like I don't really think it's all that fun, but I do it anyway because it's good for your customers, it's good for business. It's also like really good for a lot of other reasons, and there's many, many other testing talks, but like just do it. Also that 2014 paper, if people like don't believe you, show them that because that's like the trump card, it's great. So anyway, you have property-based testing. This is actually super low investment. I would highly recommend playing around with it if you've never used it. It's great. Fault injection testing, also if you're building anything that has any uptime, reliability, distributed systems requirements, just kill things on your machines. It's like not that hard. Shoot a node in production, like see what happens, try it out. This is actually gonna greatly help you stabilize your services. And then canaries are really great for reducing the risk of deploying, right? But this should sort of be like you've done all of these things and then we canary code. Okay, so briefly I would just want to wrap up and talk about like, some things about, the world kind of sucks today. We have to do all this stuff and we don't even get provably correct systems. That's a bummer. But like there is some really interesting research happening out there now that I think is actually not that far away. So these are 3 different papers that I really like. Lineage-driven fault injection is actually from Peter Alvaro, and he worked with Netflix to implement this. And so this is an idea of combining model checkers and or like reducing the space that you have to explore and then like running this with fault injection in production and tracing it back. I'm doing a horrible job of explaining it. It's linked because I'm not going to go through it. This is super cool because it's actually being used in industry right now, or they went and implemented it and it like worked. Because I'm Strong Enough is a great paper, which I'm going to go into a little more detail. I like it mostly because it has a share song. Also, it's cool, but we'll get there. It's named after a share song. And then Iron Fleet is another really cool way that they're trying to incorporate specifications and formal verification into your day-to-day programming language via your IDE that comes from Microsoft. Okay, so like I said, because I'm Strong Enough, this was also published at Popple in 2016. So basically, instead of exhaustively exploring the failure space of a specified program, and trying to do all the model checking, what it does is it actually helps you go and specify, sorry, blanking on the word. You specify your tenets of the system, like these are the properties that it should hold, and then it'll help you verify that that you are using just the right amount of consistency so that you can have more available systems and only add consensus and strong consistency where you need it. So the way you do this, and why I think this is super interesting, is because it actually is implemented in terms of like annotations on Java. This is Java code. And so you can install this, it's actually like open source. And what they do here is it's a bank example. And so what you're saying is you're defining an invariant, and you're saying like in a simple bank example where I can debit and deposit in an account, these are the annotations that I'm going to do. So you do this like in a design stage. So what it's going to say is like, okay, my account balance is an integer. The balance has to be greater than or equal to 0. This is an invariant, like that must hold. This thing must always be true in this system. And then it sort of defines the different actions that you can take, which are debit and deposit. It then goes on to say on deposit, I have an integer that I'm adding to my account balance. The amount of a deposit must be greater than or equal to 0. So then the new balance will be the balance plus the amount. So math can basically prove that this will never violate the invariant that your account goes below 0 because you're adding a positive number to a 0 or a positive number, which will always give you a non-zero number or like a positive or non-zero number. So that's cool. We don't really need any coordination around debit or adding money to your account. Where you do find that you need coordination is on debit, right? Because my amount that I'm debiting is an integer. It can be non-zero, or can be less than 0, sorry. It defines as a precondition, which is that the amount in the account must be greater than or equal to 0 to debit money from it. And then it also, once again, defines the invariant that the new balance is balance minus the amount. So then you could have, in theory, an amount that violated or that made the balance go below 0. So what would then happen is that your invariant over the balance of the account would be violated, and so that's not a valid action. So what will actually happen if you ran the size tool is that it will tell you, hey, you can't run this without some kind of strong coordination here to debit an account, because it has to check with all the other replicas to say, you know, is my account balance greater than 0, and make a debit, and like it has to hold an exclusive lock on the account balance at that point in time. So this is, I think, super cool because, right, it's taken this, like I define my invariants, I define more the semantics of what I want my application to do, and then I have this tool that helps me tell me that my assumptions are correct, that like, hey, I need coordination here, or I do not need coordination here to maintain the invariance that I've described. I also think it's cool because it's like a design doc in your code. That's super nice. And then it's also, you know, it's just like, it does have the problem of like, then you have to implement it correctly. Like, obviously it could be wrong, but at least like the documentation is right there. So this is super cool, I think, and like really interesting research. Okay, so let's wrap it up. In conclusion, you know, if you want to have a supercritical component, if you're building core infrastructure that's like powering the entire internet, maybe think about using formal verification because it does have a lot of great benefits like they showed in Amazon. Unit tests and integration tests find a ton of errors, actually way more than I expected, and I was always sort of a proponent of testing. And basically, like, try out these things like fault injection testing and property-based testing with your teams. They're super easy, they're super low cost, and they expose a ton of bugs, and and when it does succeed, it greatly increases your confidence that you can like deploy this to the wild and everything is gonna be fine. Okay, so just to wrap it up, enjoy the ride, have fun, and test your freaking code. This is a quote from my friend Camille Fournier, and I'd like to thank all these lovely people who have helped me with this talk and the article. And yeah, I'm happy to take questions now, and this is the resources link, or feel free to tweet them at me. Thanks.